On World Quantum Day, April 14th, 2026, NVIDIA did something almost nobody expected. They didn't unveil a new chip. They didn't announce a bigger, faster quantum processor. They released something considerably stranger, a family of artificial intelligence models that don't run quantum computers at all. They babysit them. And within days, laboratories on 3 continents, from Fermilab to Harvard to a national physics laboratory in the United Kingdom, quietly started using it. Read that again. The single most valuable company on Earth just gave away for free the exact software tool that multiple competing quantum computing companies now depend on to keep their fragile multi-million-dollar machines from falling apart mid-calculation. And if you run anything inside a modern AI data center, this is the story you genuinely need to understand. To understand why this specific release matters so much, you first have to understand a problem that has quietly haunted quantum computing for years, one that has almost nothing to do with the parts of this technology that usually make headlines. Everyone talks about qubit counts, about which company built the most powerful chip, about dramatic breakthroughs proving quantum computers can outperform classical supercomputers on some narrow, exotic task. What almost nobody talks about is the unglamorous, brutally difficult engineering problem sitting underneath all of that excitement. The fact that a quantum processor is, by its very nature, one of the most temperamental pieces of hardware humans have ever tried to build. Individual qubits drift out of calibration constantly, their precise behavior shifting subtly from moment to moment as temperature fluctuates, as electromagnetic interference creeps in, as the sheer physical strangeness of quantum mechanics does exactly what quantum mechanics always does, refuses to sit still and behave predictably. Getting a quantum processor to actually produce a trustworthy answer requires 2 things happening simultaneously, in real time, without pause. First, someone or something has to continuously tune or calibrate every single qubit so it behaves consistently enough to be useful. Second, an entirely separate system has to constantly watch for errors creeping into the calculation and correct them instantly, faster than those errors can spread and ruin everything. This is not chaos. This is simply the day-to-day reality of operating a machine built on physics. This delicate, and for years, both of these tasks, calibration and error correction, were handled through slow, painstaking, often manual processes that limited exactly how far quantum computing could actually scale. Here's where the story takes its first genuinely important turn. Because throughout 2025 and into the opening months of 2026, something significant shifted across the entire field. And understanding this shift is essential to understanding why NVIDIA's timing wasn't a coincidence. Multiple separate laboratories, working independently, all managed to prove something researchers had chased for nearly 30 years. Google, with its Willow chip, IBM, with its own surface code demonstrations, Quantinuum, with steady incremental progress in trapped ion fidelity. Each of these teams, working entirely separately, demonstrated that physical qubit quality had finally crossed a critical threshold, the point where a specific error correction technique called surface code encoding genuinely starts winning against noise as the code scales up, rather than simply generating more errors than it fixes. This is precisely the milestone known as below-threshold operation. And once multiple labs proved it was achievable, something important happened to the entire field's central bottleneck. It moved. For decades, the primary obstacle to useful quantum computing had been the raw physics of the qubits themselves, simply keeping them stable enough, for long enough, to do anything meaningful at all. Once that physics problem finally started yielding, the bottleneck shifted somewhere else entirely, into the classical software and electronics surrounding the qubits, the systems responsible for actually calibrating them and catching their errors in real time. NVIDIA, watching this exact shift happen in real time across the industry throughout 2025, built Ising specifically to fill that newly exposed gap. Let's walk through exactly what NVIDIA actually built, because the specifics matter enormously here. And this isn't a single monolithic product. Ising arrives as 2 genuinely distinct families of artificial intelligence models, each one engineered to solve a completely different half of this problem. The first, called Ising calibration, is a 35 billion parameter vision language model trained on an enormous body of multimodality qubit data, essentially teaching the system to look at the messy, noisy readings coming off a real quantum processor and instantly understand exactly how that processor's individual qubits need to be tuned to behave consistently. Think about what calibration traditionally required before this. Skilled physicists, manually adjusting parameters, running tests, adjusting again, a painstaking process that could stretch across multiple days for a single processor before it was ready to run genuinely useful work. NVIDIA's own published results claim Ising calibration compresses that entire process from days down to mere hours and supports what the company calls agentic calibration automation. meaning the system doesn't just suggest adjustments for a human to manually approve. It can act autonomously, continuously tuning a quantum processor's behavior without requiring a physicist to babysit every single step. The benchmark results behind this specific claim deserve genuine attention because NVIDIA didn't simply compare its model against other quantum-specific software tools. They compared it directly against some of the most advanced general-purpose artificial intelligence systems currently available anywhere in the world. Using a newly introduced benchmark called QCaliVal, specifically designed to test performance on quantum calibration tasks, NVIDIA reports that Ising calibration outperformed Gemini 3, 1 Pro, Claude Opus 4. It spreads that information across many physical qubits working together, continuously taking redundant measurements, designed specifically to catch mistakes before they corrupt the underlying calculation. Decoding is the process of taking all of those redundant, messy measurements and translating them into an actual usable correction signal, telling the system exactly what went wrong and exactly how to fix it. Here's the part that makes speed absolutely non-negotiable rather than simply a nice bonus feature. This decoding process only works at all if it keeps pace with the rate at which new errors are actually appearing on the processor. A brilliant, perfectly accurate decoder that runs too slowly is functionally useless because by the time it finishes analyzing yesterday's errors, today's errors have all. According to the company's own published results, Ising decoding runs up to 2.5 times faster and 3 times more accurate than PyMatching, the open source decoder that most quantum research groups around the world currently rely on as their default industry standard tool. And there's a third number buried inside these results that deserves just as much attention as the headline speed and accuracy figures, because it points towards something genuinely practical. NVIDIA's models require 10 times less training data than comparable approaches to reach this same level of performance. Think about what that specific detail means for a smaller quantum computing startup, one without access to Google's or IBM's massive internal datasets. A model that needs a fraction of the training data to hit competitive performance dramatically lowers the barrier to entry for exactly the kind of smaller, more specialized quantum hardware companies that make up so much of this rapidly diversifying industry. There's a more precise, more technical benchmark buried inside NVIDIA's own published documentation that's worth including here, because it moves this story beyond rounded, headline-friendly numbers and into genuine scientific specificity. NVIDIA's own published results show that its fast pre-decoder, paired with the existing PyMatching system, achieves a 2.5 times speed improvement and a 1.11 times accuracy improvement, specifically measured at a code distance of 13 and a physical error rate of 0.003. Now, those specific technical parameters, code distance and physical error rate, might sound intimidating if you're not a physicist, but here's what they actually tell you. This isn't a vague marketing-friendly claim tested under some ideal, cherry-picked laboratory scenario. This is a precise, reproducible measurement taken under a specific, clearly defined set of real experimental conditions, exactly the kind of granular, verifiable detail that separates genuine scientific reporting from empty corporate hype. Now, here's the honest, necessary turn this story needs before it goes any further, because a genuinely rigorous piece of analysis published shortly after Ising's launch made a point worth sitting with directly, one that reframes the entire story in a genuinely more interesting way than the headline numbers alone might suggest. The specific analysis stated plainly that the headline figures, the 2.5 times faster decoding, the 3 times better accuracy. The calibration process, compressed from days down to hours, are worth noting, but they are not actually the deeper story here. Read that carefully, because it's a genuinely important reframing. The real significance of Ising isn't captured entirely by any single benchmark number. It's captured by what those numbers actually enable: sustained, long-duration quantum computation. Google's Willow chip proved below-threshold error correction was genuinely achievable back in December of 2024, a milestone that rightfully generated enormous excitement across the entire field. But Willow's landmark demonstrations ran for relatively short experimental windows, scaling that same underlying capability up to the kind of sustained, hours-long, or even multi-day continuous computation that genuinely difficult, genuinely useful applications would eventually require demands something considerably harder than proving the physics works once under carefully controlled conditions. It demands decoders capable of maintaining that same real-time performance indefinitely, hour after hour, without ever falling behind the accumulating errors. A 2.5 times improvement in decoding speed doesn't just make an existing calculation finish faster. It directly raises the ceiling on how many total gate operations a quantum processor can actually sustain before its protected logical qubits inevitably decohere and the calculation collapses. Think about the difference between a marathon runner who can sprint impressively fast for the first 100 meters and one who can actually maintain a strong, sustainable pace across the entire 26 miles. Ising's real contribution isn't proving the sprint is possible. Google already proved that. Ising's real contribution is extending exactly how long that pace can genuinely be sustained. The speed with which the broader quantum computing industry actually adopted this new software tells you almost everything you need to know about whether it genuinely solved a real urgent problem, rather than simply generating an impressive press release nobody actually ended up using. On the calibration side alone, adoption within days of launch spanned an extraordinarily diverse range of institutions. Atom Computing, Academia Sinica, EeroQ, Conductor Quantum, Fermi National Accelerator Laboratory, Harvard University's John A. Paulson School of Engineering and Applied Sciences, Inflection, IonQ, IQM Quantum Computers, Lawrence Berkeley National Laboratories Advanced Quantum Testbed, Q-Kittrell, and the United Kingdom's National Physical Laboratory. On the decoding side, an equally broad, equally impressive list emerged just as quickly. Sandia National Laboratories, Cornell, the University of Chicago, UC San Diego, UC Santa Barbara, Inflection, IQM, SEQC, and a company called EdenCode. Think about the genuine diversity packed inside those two lists. These aren't companies all building the exact same kind of quantum hardware, competing directly against each other for the exact same narrow slice of the market. This adoption spans superconducting qubits, trapped ions, and neutral atoms, essentially every major competing physical approach to quantum computing currently being pursued anywhere in the world, all independently deciding, within the same narrow window of time, that this specific piece of NVIDIA's software genuinely solved a problem their own engineering teams hadn't yet solved as effectively on their own. This pattern of universal adoption, spanning otherwise fiercely competing companies, reveals something genuinely important about the specific problem NVIDIA chose to target, and it connects directly to a broader strategic pattern this channel has documented across multiple previous stories about NVIDIA's quantum computing ambitions. Calibration and error correction aren't problems unique to any single qubit technology. Every quantum hardware company, regardless of whether they build superconducting circuits or trapped ions or neutral atoms, ultimately runs headlong into the exact same fundamental challenge, keeping their fragile hardware stable and error corrected in real time. This is precisely why Ising found such immediate, such broad adoption across companies that would otherwise consider themselves bitter, direct competitors. NVIDIA didn't build a tool tailored narrowly to one specific hardware approach, hoping to lock a single company into its ecosystem. It built a solution to a problem every single quantum computing company shares identically, which is exactly why an unusually broad, genuinely diverse coalition of otherwise rival institutions all converged on using it within the same handful of days. This launch didn't emerge in isolation, and understanding exactly where it fits inside NVIDIA's broader quantum computing strategy reveals a genuinely methodical, carefully sequenced pattern of infrastructure development stretching back several months. In October of 2025, NVIDIA introduced something called NVQLink, an interconnect specifically designed to solve the fundamental plumbing problem separating quantum processors from the classical computing power needed to actually operate them, achieving latency under 4 microseconds between quantum controllers and NVIDIA's own GPUs. 5 months later, in March of 2026, that promise moved from announcement to genuinely usable software, with the public release of an application programming interface called CUDAC Realtime, finally giving developers the actual tools needed to write code, exploiting that ultra-low latency connection. And then, roughly 1 more month after that, in April of 2026, Ising arrived to fill the final, crucial piece of this puzzle, the actual artificial intelligence models, running on top of that infrastructure, doing the real moment-to-moment work of calibration and error correction that the entire interconnect architecture existed specifically to support. Think about the deliberate, patient sequencing embedded inside that specific timeline. First, build the highway. Then, build the on-ramps developers could actually drive onto. Then, finally, put an actual vehicle on that highway, capable of doing genuinely useful work. This isn't the pattern of a company chasing a single, isolated headline moment. This is the pattern of a company methodically, deliberately building out an entire layered technology stack, one carefully sequenced piece at a time, each new release depending directly on the infrastructure that came before it. And this is exactly where the second half of this video's title becomes genuinely relevant, because everything described so far connects directly back to the exact same physical infrastructure already running inside AI data centers around the world right now. Ising isn't some exotic, standalone piece of hardware requiring an entirely separate, specialized facility to operate. It's a piece of software running on NVIDIA GPUs, the exact same category of chip already filling data center racks from Virginia to Singapore, currently powering the artificial intelligence boom. This channel has covered extensively across previous videos. Think about what that specific fact actually means for anyone responsible for planning or operating that infrastructure right now. The same GPU fleet already handling ordinary AI training and inference workloads can, without requiring an entirely separate category of specialized hardware, also run the exact AI models responsible for keeping a nearby quantum processor calibrated and error-corrected in real time. NVIDIA's own quantum product lead, in comments covered in earlier coverage on this channel, described this shift in strikingly direct terms, explaining that artificial intelligence is becoming the control plane for quantum hardware because qubits are noisy, and the only realistic way to manage that noise at the scale this technology genuinely needs is through AI models exactly like these. This directly reinforces the broader hybrid quantum classical data center trend this channel has tracked closely across multiple previous stories. The Open Compute Project's formal white paper series on physically integrating quantum processing units inside existing data center architecture, Microsoft's own quantum processors specifically engineered to fit inside standard server rack footprints, and IBM's decision to run an actual quantum computer physically alongside a classical supercomputer inside the same facility. Picture what this actually looks like inside a real physical data center once this entire layered stack comes together as intended. A single facility, filled predominantly with ordinary GPU racks handling the everyday work of training and running artificial intelligence models, the exact workload dominating headlines, and consuming enormous amounts of electricity right now. Somewhere inside that same facility, a smaller cluster of quantum processors sits connected through NVQLink's ultra-low latency interconnect. And running continuously, quietly in the background, Ising's calibration and decoding models draw on exactly the same underlying GPU infrastructure already installed throughout the building, dedicating a small, specialized slice of that computing power specifically to keeping the nearby quantum hardware stable and error-corrected, rather than requiring an entirely separate, dedicated facility built from scratch. This is precisely the layer cake model of data center infrastructure that industry insiders have started describing across recent coverage. Each new technological wave, cloud computing, then artificial intelligence, and now quantum computing, adding itself directly on top of the classical infrastructure that came before it, rather than tearing that existing foundation out and replacing it entirely. It's worth being genuinely honest here about exactly what remains uncertain, though, because responsible coverage of any technology this new demands the same careful scrutiny this channel has applied consistently across every previous story in this series. Industry analysis published in the weeks following Ising's launch offered several specific, falsifiable predictions worth tracking as this story continues to unfold. By the end of 2026, at least 3 publicly traded quantum hardware companies are expected to fully integrate Ising decoding directly into their production computing stacks, with Rigetti, IonQ, and Quantinuum specifically flagged as the most likely candidates to move first. These are genuinely testable claims, the kind that will either prove out or fail to materialize over the coming months, and tracking whether they actually happen offers a far more honest measure of Ising's true, lasting impact than simply repeating the impressive headline benchmark numbers from launch day. It's also worth being precise about exactly what Ising is, and just as importantly, what it explicitly is not. This is not a quantum chip. It doesn't add a single additional qubit to any existing quantum processor anywhere in the world. It's the AI substrate running underneath that hardware, helping other companies' quantum processors work more reliably, a genuinely important but fundamentally supporting role rather than a headline-grabbing hardware breakthrough in its own right. Think finally about what this entire story ultimately reveals about where NVIDIA's actual strategic advantage in quantum computing genuinely lies, because it's considerably more interesting than a simple story about building faster chips. NVIDIA isn't betting its future purely on which specific quantum hardware architecture eventually wins this ongoing, genuinely uncertain race between superconducting circuits, trapped ions, neutral atoms, and photonic systems. It's betting on something structurally different and, in some ways, considerably safer, becoming the essential, universally adopted software layer that every single one of those competing hardware approaches ultimately needs to actually function reliably, regardless of which specific technology eventually proves most commercially successful over the coming decade. This is precisely the same underlying strategic pattern that has defined nearly every major NVIDIA quantum announcement covered across this entire video series. NVQLink positioning the company as the essential interconnect standard, regardless of which qubit type ultimately wins. And now Ising positioning the company as the essential intelligence layer, keeping all of those competing qubit types functioning reliably in the meantime. Whether Google's superconducting approach, Quantinuum's trapped ions, or some entirely different architecture still sitting quietly inside a university laboratory eventually emerges as quantum computing's dominant long-term technology, NVIDIA has methodically positioned itself to matter, regardless of which specific horse ultimately crosses that finish line first. If you want to understand exactly what happens once Rigetti, IonQ, or Quantinuum actually confirms integrating Ising decoding into their live production quantum systems, the specific milestone that would genuinely validate the predictions currently circulating throughout the industry, that's precisely the story we'll be tracking closely as it continues to unfold, so make sure you're subscribed before that confirmation finally arrives. Before you go, I want to know what you honestly think about everything you've just heard. Does NVIDIA's decision to release this specific software completely open source, free for any competing quantum hardware company to use, strike you as a genuinely generous contribution to accelerating the entire field forward? Or do you think it's a carefully calculated strategic move designed to make the entire quantum computing industry permanently, quietly dependent on NVIDIA's infrastructure, no matter which specific hardware technology ultimately wins? Leave your honest answer down in the comments below, and as always, I read every single one.